share a story that we've been working on in the past 10 years about how to make extremely robust and conductive, adhesive, and flexible, stretchable, even washable metals for flexible electronic or wearable electronic applications in general. So I think that the key idea is in the past roughly 20 years, soft electronics really start to change our world, right? So we have tons of new applications, from flexible displays, electronic skins, robotics, bioelectronics, to textile electronic textiles in the recent 20 years. And this area is believed to be a key driving force in the next 20 years continuously. So as a material scientist myself by education, we find a common need for this soft electronics or this soft metal electrodes. Okay, and why metal? I think for those who with devices or systems with previously, you know that metal is almost kind of indispensable for all this device, and partially it's because of the high conductivity, the good stability, the cost effectiveness. They are very understood in terms of device physics. You know which metals to go for a good device. You know how to match them for a good system. And at the end of the day, metal, even though it's very rigid, but if you make them thin enough, small enough, they're very flexible actually. They can even be foldable, stretchable, and washable if you engineer them in the right structure with the right interface. So we believe this is critical to make the success story for the soft electronics. But if you look into how things are made, how this metal electrode made conventionally in the semiconductor industry or this new printed electronic industry, they're basically made in two ways. One is vacuum deposition, for example, thermal evaporation, electron beam evaporation, sputtering, or in another way, you use some kind of nanoparticle inks or microparticle inks, and then formulate it in a certain way that you can print it on top and then sinter them by heating up or by kind of a localized melting or laser melting. Then you can merge them together and form this so-called metal electrodes. And that has been done in the last 20, 30, or 50 years in industry and also in the academic. The problem, however, is that when you come to a soft electronic or flexible electronic in general, you face another issue, is the interface. There's a huge mismatch in terms of materials between the electrodes, which is made of metal, on top of the plastic substrates, or it's sometimes elastic substrates, which is made of polymer. And this metal polymer is known that they don't like each other most of the time, that there has a serious mismatch at the interface, right? So once that, for example, metal is rigid and plastic is very, very soft. So in this case, they may crack or they may form very high stress at the interface, and so that they fail very easily. They form cracks, for example, upon some sort of bending. That's well known to the field. Another other issues arise from this may be like after you crack, they may fracture or they may form very rough surface, and etc. etc. So actually, the challenge for fabricating soft metal electrode in our field has been quite critical, I would say, or one of the major issues in the field. Can it be produced in a vacuum-free technology, because we're using plastic, using polymer, and polymer generally does not like vacuum environment? Can we produce low-cost electrodes such as copper and nickel that we use all the time, but not something very expensive? For example, in this printing process, typically you need to use silver and gold, which is very, very expensive. Right? Can we process temperature at low temperature, because the polymer substrate it cannot tolerate very high temperature? Can we make it thin enough, smooth enough, so to yield very high performance sinting devices, which is quite critical? Can we have some good interfaces between all this material, for example, the substrates, to have good adhesion? Can we have the good interface with the active material so that they can perform better? Right. So with all these problems, actually having a good, high-performing soft metal electrodes has been quite a challenge in the last 10 or 20 years. So this is what we've been really working on. To address this question, we developed a technology or a chemical approach we call a polymer-assisted metal deposition, which actually grow a metal from a bottom up versus the top-down approach that I showed you just now. So basically, the idea is to modify the substrate, whatever substrate, with whatever structure, with thin layer polymer. And this polymer is designed in a way that it allows you to immobilize catalytic moieties, which allows you to do a electrolysis deposition. So that's a reduction process in the chemical and liquid environment of metal. So that basically is that you start to modify the substrate with a polymer, which allow you to grow a metal from bottom up to form this very, very soft, adhesive, and highly conductive electrodes, metal electrodes, right? So I'll give you a very specific example of the chemistry. So basically, this is how it look like. You can start to grow this polymer, and this, in this specific case, it's a cationic polymer, so nitrogen plus. So this is nitrogen plus, which allows you to absorb these anions, right, and which allows you to deposit metals from bottom up through a electrolysis deposition process. So this is very unique, very easy to do in a room temp environment. So change this chemistry to apply it onto some soft substrate, for example, textiles, fibers, yarns, and fabrics. So you can do all this nice coating of metals, right? So we started to grow the polymer, right? And after we grow the polymer, in this case, we deposited copper, okay, which is typically very difficult to deposit. As we can get some copper yarns, fabrics, and if you zoom, you will see that in every single cotton fiber, right, a thin layer of metal, in this case 300 nanometers thick, conformally coated on top, no matter how the structure of the cotton look like. Cotton is typically very irregular, okay, but it's despite the topography, you can actually coat a nice layer on top because the growth was from bottom up. And the key thing is that the conductivity is great, the resistance is really, really low, and the adhesion is great. We can go for commercial laundry, so you can go for like a laundry machine wash for 40 minutes at 40 degrees Celsius with detergents and dry it, wash for 40 minutes, that's one cycle, and dry it, and then wash many, many cycles, no problem. So we developed this. And this nice thing about this PAMD or PAMD is that it can also be compatible with printing technology. Right? This is a homogeneous coating. So if you combine with a printing technology, you can pattern the electrodes. Right? So I'll show you that one of the work that we published in 2016 that we developed some polymer ink, which is dissolvable in alcohol. And so that you can use that ink to place in the cartridge of a commercial desktop inkjet printer and print onto commercially available like PET sheets, right? Just like inkjet print, right? So after you print it, let me see if I can speed up a little bit. You don't really see, you see a little bit of kind of pattern, right? So we go for a curing process to cure the material under UV. And then we'll place this polymer, right, onto the electrolysis deposition bath of copper to grow the copper. And this growth takes about like minutes to tens of minutes. So what you get here, this specific example is that roughly 70 nanometer thick copper. And this is very shiny copper. You know the copper is in metallic gray, very conductive, very smooth, and very continuous. And it's very flexible, right? Of course, you can engineer, you can ask the computer to print out different kind of more complicated structures on demand. So this is really nice, right? So you can print different structures with different printing technology at different resolutions onto different substrates. And then by controlling the electrolysis deposition chemistry, you can produce different kind of metals of interest, right? So basically it's kind of very powerful tools that allows you to make soft metal electrodes with a specific structure onto a wide variety of substrates. So how's the conductivity look like, or the resistance look like? So basically, the conductivity we measure, the thin film is about one of the really, really best reported ever through electrolysis deposition process. So the 10⁻⁷ Siemens per meter. But the key thing is that when you bend the material on top of a flexible substrates, they don't get destroyed, right? So this PAMD is the one that grew by our method. And these are done through a typical kind of an electrolysis, through a vacuum deposition process. So you see the vacuum deposited one has lots of cracks. When you bend a different kind of radius of curvature, in our case, we don't see any cracks. These are not cracks. These are just buccal films because we bend many, many times. So we can bend it like a few dozen times. Actually, we can build a few tens of thousand times. The resistance doesn't really change much. It roughly changed by 5%. And this typically because of a slow oxidation of copper in the air. It's not because of the material cracking or any other issue. And so this is great. It's very crack-free, and they don't fracture, they don't come off from the surface. And if we measure this unpublished result, if you measure all this, you will find that the reason why it has this high stability is because this case one is our PAMD made material, is that because they have a very high low at crack initiation. That means it's very difficult to form cracks. Okay, and it also has very high low at film fracture. That means once the cracks are formed, they are very difficult to fracture, right? So that these two properties ensure the high stability of our PAMD made polymer. But if you look at those without a interlayer or without those normally reported as thermal evaporation layer, the values are much, much worse, and therefore they crack or they form cracks much easily or fracture much more easily, right? So that's kind of a kind of information that we come up with this, that basically to wrap up is basically a PAM is a process which allows you to grow a metal from bottom up through a interlayer of polymer, right? And then in this interlayer, they form this kind of organic, inorganic composite structures, which allows you to adhere the metal, whatever grow on top, very firmly onto the substrates, right? And then the key thing is here is this, the growth is very versatile on whatever substrates, and you can use it for many, many different kind of metals at low temperature. So that's very, very suitable for soft electronics in general. So I would say we've been working this for 10 years. So we work on many, many aspects, right? As we summarize this on this paper in the advanced material invited progress review in 2019, late 2019, and we published this. To summarize, how do we play around with the chemistry, with the materials? How do we play around with the printing technology? That's the lithography part. How do we play around with the base material so that you can develop different kind of metallic electrodes that will be used for different applications? This includes like planar structure or porous or fibrous or multi-scale topography, right? And with this enabling chemistry and printing technology and materials, we're actually been working with a wide variety of devices to show that this metallic electrode are very versatile, very powerful. It can be used in energy storage, can be used in sensors, it can be used as a thin devices such as LED, transistor, and solar cells. I'm going to give you very quick kind of a snapshots of some of the applications, okay, due to the time limit. So this is the one that we use for organic solar cell. Right, so the key thing is here is we use this as the opaque electrode. So copper as opaque electrode for solar cells are rarely reported through a printing process, and the reason is because of if you print a copper ink. For those who work with copper ink, they know copper ink is very difficult to print because it's easy oxidation of copper and then a low conductivity. And if you use it for organic solar cell, you know that the roughness is a killing factor. It's very, very rough if you print particles. But in our case, if you do it at the PAM, the conductivity is no problem, as I demonstrated before. The roughness is very low as well. The roughness is about 6 or 7 nanometers, which is very close to the substrate roughness. And therefore, we can use this low roughness electrode as a bottom layer of opaque electrode, and then you sprinkle whatever materials on top and to finish the entire device, right? So then we can come up with a device with a very similar performance if we compare to those devices fabricated through evaporation and vacuum technology, right? Very, very similar result. This was an organic device. But the key thing is the flexibility is way better. So we bend the device, one with the printed electrode, one with the evaporated electrode, and the one with printed electrode, there's no problem at all if you bend it 1,000 times. But for the one with evaporated electrode, then they actually fail after like 400 or 500 times, right? The entire device goes down and die immediately. And the reason is because of formation of cracks. So the bendability of the device is way better, and the performance was not sacrificed. That's the key message right here. Of course, we can push it further to do some sort of a transistor where we actually printed this copper and source and drain electrodes, and then we do all the semiconductors and insulators, and then print another top gate, right? So it looks like this. So in over 4-inch wafer with different kind of channel length. We show that with this low temperature printing and processing, the transistor looks actually pretty good. Good mobility versus a good on-off ratio, very low threshold voltage, and then on the nice SS. Okay, a little bit of hysteresis because of the low temperature processing that is in principle it's very difficult to get rid of the hysteresis in the semiconductor and the contact. Bendability again is no problem. We can bend it at least to a very small rate of curvature, like 8 millimeter, and then something like a big thumb, and then 1,000 times again. The device actually does not look worse, or it actually go better. Okay, so I will spend another like a short few minutes to show you that we can actually also apply this on battery and capacitor. So the idea, and just now I showed a thin film device, like a semiconductor device. We can use it for energy storage device as well. And the idea was very simple. Because for batteries, typically it's built with a very simple structure where there are two pieces of metal foils on which there are some electrode or so-called active materials are coated. And these two electrodes will be paired and separated with a layer of so-called separator. Yeah, and that's basically how a battery will look like, or a capacitor will look like. Of course, those are filled with electrolyte. And so our idea is to use our fabrics or yarns to replace these metallic foils to enable flexible sort of battery and capacitors. Okay, so we use conductive textiles to do that. So I think I'll show you that we'll be able to do yarns using the PAMD process. And then once you got yarns, you can do weaving, you can do knitting, you can do stitching, you can get fabrics if you want with different structures. So in this paper, 2018 paper, we showed that you can actually use this idea to build very, very high energy density lithium sulfur batteries. At the same time, they're extremely flexible. Okay, so we started with this fabric, common fabric. We deposited copper or nickel. The copper is for anode of lithium metal. Nickel is for sulfur. That's the sulfur cathode. And then you can have this anode look like this, right? So basically, this is a cross-sectional structure of how the lithium metal deposited on the copper-coated carbon fabrics. And the key thing here is that every single fiber was coated with very nice layer of lithium metal, right? And when you cycle the cell, when the cell is used as an electrode and then you electrochemically charge and discharge it, you see that at the very beginning, actually, there are lots of micro patches, which is not good at all. But once you cycle, it's getting better and better, more uniform, right? So it's getting, actually, this micro patch structure will disappear. It comes up with a very thin, uniform films are coating on top of the electrode, which is great because the key issue of lithium metal is that the formation of dendrites is aggregation of microstructure. In this case, we don't see any dendrite formation. Therefore, the device should be very, very stable. So you run for a long-term stability test, you see that over potential has been kept very, very small and has been very, very stable, even at high this kind of current density, right? right, at 5 ampere per centimeter square, which is considered really, really high. The device, the electrode was still very, very stable. If you compare the black curve, and this is the control device, they form lithium dendrite, and the device will actually short very, very easily. Okay, and this is the cathode side. We also can do the same trick to load the sulfur very uniformly on every single fiber and enable this high rate and high stability performance. I'll skip this part. And so basically, if you pair this cathode with the anode together with a separator, then we can come up with a very high energy density lithium sulfur battery. At the same time, they are very, very flexible. We can even fold it. Okay, we can even fold it, and the device doesn't really fail. There is some kind of deterioration of the capacity, but they don't fail immediately. And they show that the reason is because of this high stability of the anode and the cathode, and also the good flexibility of both. Okay, to enable this high energy density at the same time, the good flexibility. So I'll show you a few kind of clips showing how flexible the battery is going to be. This is a lithium metal battery. It can be used to power quite a lot of electronics. So it can be folded, it can be crumbled, it can be hammered, it can be trimmed, right? So it's quite safe, very soft device. Right, we collaborated with this idea with a few professors. This is Professor Dan Wang from Chinese Academy of Science. So he's been a leader in this multi-shell materials. So we use our kind of concept and use electrodes for his vanadium oxide cathode. And at the same time, we actually tackle the stability of the problem of the cathode and the flexibility of the cathode. So we can make something really flexible. Similarly, we also tackle the problem to work with Professor Yongming Tang, also in Chinese Academy of Sciences, for his dual ion battery anode. So we tackle the problem of his silicon anode, which is being used in the dual ion battery. Again, we can make very flexible cell, at the same time improve the stability of the cell. So I think this is quite a unique and powerful idea of using kind of fabric-based or textile-based kind of a material to replace this metal mesh or metal foil-based in a typical lithium-ion battery. And we recently published this jewel paper. It's a commentary paper to discuss how we should actually compare and benchmark all the literature reported flexible batteries in one equation and one diagram. We call this a figure of merit for flexible batteries. If you're interested, please read this in detail. It tells you that if you can measure your areal energy density, which everybody can, and then the bendability and the bending radial curvature, which everybody will report, and then doing this equation, you come up with this. You can put your data into this graph, right? So the higher the figure of merit, the better the performance of flexible battery, means higher energy density and better foldability, or better flexibility. So the fabric one, we compare all the literature using the same active materials. The fabric one will be better than paper one, and paper one will better be the metal mesh. And this is where the commercially available one over here. Okay, so we'll tell you the commercial one, the rigid one, is not suitable for metal flexible application, but the fabric one will be very suitable. At the same time, can keep a very high energy density actually. So we use a similar concept to work on supercapacitor. Okay, so we have quite a few of publication on this as well. Again, tell you that using this textile-based structures and materials will allow you to have very high performance supercapacitor, at the same time very high flexibility and even foldability. And in this case, we show that you can use additive kind of embroidery-based technology to manufacture or fabricate this high-performing and even washable supercapacitors. So I would like to summarize the PAMD. If you still remember, it's called Polymer-Assisted Metal Deposition. It's a bottom-up process which allows you to grow metal at a very low temperature and grow the metal that you need, not the expensive one, and with good adhesion, so very, very adhesive, great conductivity, and then it's capable or compatible with many printing technologies, so that you can produce many, many devices, because you can have many, many structures or material compatibility through the PAMD. So we believe this is quite compatible with, nowadays everybody use this nanoparticle approach. This is a compatible approach, right? A complementary approach that each has their advantages and disadvantages. So I would like to thank my students and postdocs working in the projects, of course, our collaborators working on various projects in the past couple of years. Thank you very much for attention. I think I want to borrow 1 minute to talk about just the journal that you have kindly introduced. So we have this flagship EcoMat in the late 2019. The journal is a target of the journal is the flagship journal for green energy and environment, published by Wiley, APC free. So that means author do not need to pay for anything, and reader does not need to pay for anything. Our first target impact factor is 20. It's getting great. We will have, in principle, our first impact factor in the coming year, next year. Okay. For this year's data that we compare to previous one, the citing of each paper in average is more than 12. So that means the impact factor will be more than 12 in principle, right, for this year. So in next year, we believe this number will be double. Typically, that's what happened in a kind of citation trend. So we believe we will be hitting this target very easily. So the paper will aim for publishing the most cutting-edge materials in the field of energy and environment. So our benchmark within the Wiley will be anything published in advanced material, advanced energy material will be suitable to our journal. So the journal will handle in a very different way as a conventional Wiley journals. These are handled by academics. So everybody is professors in the field. Gasong-Bin Wang from Northwestern University in the US, Sang Yu Sok, Eunice in Korea, Hui-Jun Zhao from Griffith University in Australia, Qiang Zhang from Tsinghua University in China. Right. So these are all like great leaders in the field, in their respective field. I'm the editor-in-chief handling the assignment of papers to the manuscript to the associated editors. So this is our international advisory board from everywhere in the world. We just expanded the board a couple like this month. And so I welcome you to have a look at the paper. The quality is really high, we believe. And I welcome your submission, of course. And I thank you very much for your attention to my talk. And